This presentation introduces SFR-Net, a steering fusion refining network designed for multi-label zero-shot sewer defect detection. The paper addresses the realistic case where some defect categories have no training samples, yet the system must still recognize them. The core idea is to progressively reduce visual semantic ambiguity through representation steering, multi-granularity evidence fusion, and relational score refining. The paper formulates sewer inspection as a multi-label recognition problem because several defects may appear simultaneously in one image. This domain is particularly difficult because collecting and annotating defect data is costly, and some important categories are extremely rare. That motivates multi-label zero-shot learning, where the model uses auxiliary semantics to recognize unseen defects without requiring direct training samples. Existing MLZSL solutions do not transfer well to sewer inspection. Attribute-based methods require labor-intensive manual definitions. Word embedding and vision language approaches inherit a large domain gap because sewer imagery is visually very different from common pre-training data. Even prompt tuning approaches remain limited when the image encoder is effectively frozen. The paper summarizes these issues as visual semantic alignment ambiguity in a harsh, fine-grained industrial environment. The motivation slide focuses on the semantic side of the problem. Instead of relying on a short generic template, the authors ask an LLM to generate 2 text forms for every defect, a detailed domain-specific description and a concise explicit phrase. According to the paper, this bridges the semantic gap, improves alignment quality, and provides better inputs for both the clip text branch and the graph-based score refinement module. The contributions are straightforward. First, the paper proposes SFR-Net, a 3-stage framework tailored to multi-label zero-shot sewer defect detection. Second, it introduces 3 modules that target domain adaptation, multi-granularity evidence integration, and relation-aware score correction. Third, it provides the WZ-pipe dataset for this task. Finally, the empirical results on both sewer ML and WZ-pipe demonstrate clear advantages over prior multi-label zero-shot baselines. This slide summarizes the complete pipeline. SFR-Net starts from a clip dual encoder. The representation steering module inserts lightweight trainable blocks into each transformer layer so the features progressively adapt to sewer imagery. The multi-granularity evidence fusion module then combines global and local visual evidence to produce initial predictions. Finally, the generalized relational score refining module learns a transferable correction function over category relations and refines the scores. Here the paper combines better semantics with better feature adaptation. The LLM generates richer defect descriptions, while representation steering adds lightweight bottleneck-style residual modules to the clip encoder layers. These modules learn domain-specific corrections and are added back to the original transformer outputs. The authors argue that this progressively steers the representation toward sewer imagery while avoiding the catastrophic forgetting that appears in aggressive full finituning. The second and third modules operate after the steered features are available. MEF separates prediction into a global path and a local path, then fuses both scores to preserve fine-grained evidence that may be lost by simple CLS token matching. GR then models category relations using explicit phrases, builds a semantic adjacency matrix, and applies a graph convolutional correction to the initial scores. This enforces more logical and transferable predictions, especially for unseen categories. The experiments use 2 datasets. Sewer ML is the public large-scale benchmark with 1.3 million images, and WZ-pipe is the author's private dataset with 63,978 images. In both cases, the 5 least frequent classes are treated as unseen for the MLZSL setting. Evaluation follows a ranking protocol with map and top K precision, recall, and F1. The backbone is clip VIT-B/16. Trained for 8 epochs with the hyperparameters reported here. On the public sewer ML benchmark, SFR-Net delivers the strongest overall results. The paper reports 12.58% map in the MLZSL setting and 43.28% map in the generalized MLGSL setting. It also achieves the best F1 metrics. The authors emphasize that the MLZSL map is more than 2.4 times higher than the second best method, which suggests a substantial improvement in recognizing unseen sewer defects. The results remain strong on the private WZ-pipe dataset, which better reflects the target sewer domain. SFR-Net achieves 9.88% map for MLZSL and 37.42% map for MLGSL. The paper highlights that the generalized setting is nearly 38% better than MKT, showing that the method transfers well even in a more challenging dataset with scarce and long-tail defect categories. The ablation study explains where the improvement comes from. The representation steering module provides the largest jump in generalized performance, pushing sewer ML-MLGSL map from 9.92 to 39.62. MEF and GR continue to improve the results, and the rank loss gives the final boost. The semantic ablation also shows that LLM-enhanced descriptions outperform both a fixed-base template and manual descriptions. At the same time, the reported learnable parameter count is only 6.05 million. The qualitative GradCam analysis supports the quantitative results. In both seen and unseen categories, SFR-Net concentrates attention more accurately on the defect regions, while RAM often produces scattered or unfocused activation maps. The paper points out that this is especially important for complex sewer imagery containing defects of different scales, because robust localization indicates stronger visual semantic interaction and more discriminative features. To close, the paper thanks Wenzhou Water Group and Zhejiang Xinyu Technology Group for assistance in data collection. Thank you.